Okay, so that was vanilla linear regression. Let's look at what we call ridge regression, which is when we put a Gaussian prior on the weights of our linear regression model. So one issue with linear regression is they can easily overfit. That's especially a problem when we look at linear regression in the case of, one issue is when we have many features per example, more than we have examples. Another is the case where we have, when we're doing polynomial regression with high degree polynomials. So let's look at our model again. We have y is a function of x, and then let's, just to be explicit about this in our model, that relationship is also depends on w. And we can write this in plate notation, where we have many examples of x and y and just one w. So one way to counter that overfitting is by putting a prior on w, or equivalently adding regularization to our optimization problem. So if we put a Gaussian prior on w, that is, we imagine that w is distributed according to a normal distribution with mean 0 and variance 1 over tau times the identity matrix. By the way, I think, unless I'm missing something, I think there's a typo in the textbook, or they have some notational issues. I believe they mean for this is, in the textbook, this is 1 over lambda. I believe it's supposed to be 1 over tau. Just a heads up about that. Okay, if we put this prior on w, then we get this expanded objective. We have our residual sum of squares term that we had last time, plus we get this extra term that comes from the prior over w, which we can write either like this, or you'll often see it written like this, where we have lambda. This is equal to sigma squared over tau squared. This is a measure of the strength of the prior. So we can look at it as the relative uncertainty about the observations, sigma squared, versus our uncertainty about our prior on the weights, tau squared. So higher lambda means stronger prior, stronger regularization. And we have here the 2 norm of w, which is this thing here. Let's see how we can optimize to get an estimate for our weights in the case with the prior. This is going to look very similar to the normal linear regression case. So we're going to take the derivative again with respect to w. And this is going to look very similar. So we get the same terms from our residual sum of squares term. The only difference is when we take the derivative of our prior term, notice that this is very easy to get the derivative of, just w transpose w. The derivative of that is 2 times lambda times w. So now when we set this to 0 and solve for w, notice that now we have 2 terms involving w. We have our x transpose x term and our lambda term. So we're going to do the same thing before, bring those to one side and multiply on the left. That thing that we have to multiply by ends up being the inverse of x transpose x plus this additional term that comes from our prior, lambda times the d-dimension identity matrix. So when we add this prior, we get this small, kind of easy to understand modification to our MLE estimate. what we're doing now is we just additionally add to the diagonal of this matrix that we're about to take the inverse of, we give it a stronger diagonal. That's going to lead to us choosing smaller values for our W parameters. But the advantage of this is we retain our closed form estimates. We still get this analytical form for W. Although, by the way, a lot of those numerical issues that would cause us to use some of those other optimization methods, those still apply in the case of ridge regression. And again, we're not going to talk about those here. So let's see how adding this L2 regularization to our linear regression helps us with overfitting. So we're looking here at a polynomial regression. We have, I believe there's 21 points here, and we're going to look at a 14-degree polynomial. And you can see if we just fit a 14-degree polynomial to these 21 points, we get kind of this funky thing that definitely looks like it's overfit. But as we increase our L2 regularization strength, the overall magnitude of our weights is going to come down, and we're going to end up getting a smoother fit to our points. So here we've increased it by a little bit, and here we've increased even further, and we're getting this extremely smooth, looks like very close to what we'd get from like a degree 2 polynomial fit. So one way to choose our L2 regression strength is using cross-validation. That is, we evaluate our mean squared error or residual sum of squares, two names for the same thing, on a test set, not in our training set, or a validation set if we want to save our test set for kind of a final check. As we increase the strength of regularization, notice that the training error will always increase, because when we regularize with very low weight, that lets the model fit the data as closely as it wants. But as we increase the regularization, notice that at first our error comes down, and then as we increase it to the point where the model almost can't learn anything, then the weight comes back up. So a common way to choose that regularization weight is to find the minimum on the validation set. By the way, one small note is that it's we generally don't apply our regularization to the W0 weight. That is the weight for the intercept. That's not going to help us fight overfitting.